Okay, back to just finishing up this problem. We started with the inclined plane. We've really done by far the hardest part of this, and now I left you with the chore of calculating the acceleration in your calculator. The nice thing is that there's a common factor of 8 which can cancel out here, and so the acceleration is just 9.8 times the sine of 25 in meters per second squared in SI units. So when I calculate that, that's 4.14 meters per second squared. That kind of makes reasonable sense. You know, if something is falling in free fall, it accelerates at 9.8 meters per second squared. That would be like an inclined plane that's tilted up to 90 degrees. If the inclined plane is tilted to smaller and smaller angles, we would expect that 9.8 to get smaller and smaller. So here it's a moderate angle. We've got less than half of the acceleration rate of free fall. Seems somewhat reasonable. Now we're supposed to also answer how far it moves measured along the plane in the next 2 seconds. And so that seems like we want to know what x is 2 seconds later. So let's define the time just after release to be t equals 0 and the final time to be 2 seconds after that. And it seems like we just want x as a function of time. We can plug in t equals 2 seconds. So here's my x as a function of time kinematics equation. I could maybe, it doesn't really matter, but I could say the place where it's released, let's place the origin there. I wasn't really careful about it, but we could say it's released at x equals 0, so that would be 0. It's released from rest, so Vx initial or Vx0 is also 0. Those first two terms can go to 0. So x final, which is how far it's moved since it was at x equals 0, is just 1/2 ax t squared. Ax is not 9.8 here, or minus 9.8. Ax is the acceleration we just found. That's how fast it's accelerating. So I plug in t equals 2 and the acceleration that we have, and we get 8.28 meters. We're assuming this ramp is long enough that there's actually room for it to accelerate that far without going off the end of the ramp. Okay, let's, we've got to march through several different kinds of forces that we get familiar with, and we're going to do some problems where different objects are connected by strings. So here's a situation where we're pulling with a certain force, so we've got a frictionless plane here, and there are two blocks that can slide without friction on that plane. It's like they're on really slick ice. These two blocks are connected by a string, and then we're pulling on this string with a 5 Newton force. And we're asked some questions about it, including which block has the larger acceleration. We'll get to those later, but before we do, we need to talk about some properties of strings and the notion of tension, which you may not be precisely familiar with. So these are some properties of strings, and later on we're also going to talk about pulleys. We don't need that for this problem, so we'll wait. You can always count on these in Physics 110 to simplify your life, but they might be called into question in other physics courses. In other words, they're not fundamentally true, but we're always going to assume these sort of idealized kinds of strings in Physics 110. So we're going to only look at strings, or sometimes we'll call them cables or cords. They all mean the same thing. We're only going to treat strings, cords, or cables that have a negligible mass compared to the objects that it connects at the ends. So, string, a 10-inch piece of string has a certain mass, but it's usually small compared to if you connect it to a block of wood or iron or something like that. So we're always going to pretend that the string is completely massless. That's an idealization. The second property is that they have a uniform tension through the length of the string between the attachment points. In other words, you have a sense, intuitive sense, I hope, that tension means how taut the string is. The more taut it is, the higher the more you're pulling on the ends, the higher the tension. Well, if I had a really heavy cable that I hung from the ceiling, the tension would be very small at the end of the cable, but it would actually get bigger and bigger as I went up in the cable because there's more cable hanging from the bottom of it pulling down, so it's got to pull upward more. Since we're assuming that the string or cable has negligible mass, it's reasonable to also assume, and you can always count on this on the problems we're going to do in Physics 110, that there's only one tension for a piece of unbroken string. So this string has a certain tension. I might label it by T. So So I might say, here's a length of string that has tension T1. It's the same here, 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 and here. Now, all bets are off when I go through a piece of mass. So here's another piece of string that has the same tension all the way through, but it might be different than T1. So I call it T2 here. Okay, but there's no difference in where we are in an unbroken piece of string. Finally, what does the tension mean? If somebody tells me, well, a tension is a kind of force. It has force units. So a tension would be something like we place a 3-unit tension in this string, and that means it's pulling. It's pulling on the objects that are at both ends. And what the tension means practically for us is that if it's a 3-Newton tension, that means it's pulling on the objects at both ends with 3 newtons of force. So this string, if this were a 3-Newton tension in the top string, it would be pulling down on the ceiling with 3-Newton force, and it would be pulling up on mass m1 with a 3-Newton force. And if this tension down here were 2 newtons, it would be pulling down on m1 with 2 newtons and up on m2 with 2 newtons. Okay, and when all 3 of those are satisfied, we're just going to use a shorthand for that as a light string or a massless string. You can assume always in Physics 110 we're going to use these idealized kinds of strings only, not massive cables where the mass of the cable really makes a difference as you move along the cable. Okay, so that tension, you can think of the tension as just telling us how hard the string is pulling on the sides. And that's useful for us because those how hard you're pulling on the side might come into a free body diagram. So let's look at that now, back to this problem here. A lot of questions I'm asking associated with this setup. So we've got persons pulling with a 5-Newton force to the right on string 1. The string is attached to block A, which has mass 1 kilogram, which is in turn attached with another string to block B, which has a mass of 2 kilograms, and they all slide without friction. And so what's going to happen if this thing's at rest and I start pulling with 5 newtons of force? It's going to start accelerating faster and faster as time goes on if I keep applying that 5-Newton force. Okay, let's take the questions one at a time and do the first few together. Which block has the larger acceleration, block A or block B? And then we're asked to figure out the acceleration of block B. That's just part A question there. There's always a lot of controversy around this when we discuss it as a class, and the correct answer is they both have exactly the same acceleration. And that's easy to see once you see it the right way. This string, we're going to assume, I guess I should have put it in my string slide, that these strings are never stretchy either. They're supposed to be, they're not allowed to stretch at all. They only have a certain fixed length to them. So when these objects A and B start moving, they're always moving kind of as a unit. In other words, at every time they have the same velocity. Now that velocity is changing as time goes on, but the rate of change of the velocity is the acceleration. And if they have the same velocity at every time that we can watch this for, then the rate of change of their velocity or the acceleration will be exactly the same for these two. It's just like they may as well be 2 halves of the same object. They're moving as a rigid unit here, so there's no difference in the acceleration if they're moving kind of as one unit. So the acceleration is the same. Now, how do I find the acceleration of block B? Well, there's a trick we can apply. So both are the same is the first thing, and now we're going to find the acceleration of block B. What I'm going to do is a trick that's very useful, and you're going to want to remember to use it in problems like this, where you've got multiple objects that are interacting either by a string or pushing up against each other. If this object has a certain acceleration, and this one has the same acceleration, I could just as well treat this as one big 3-kilogram object. And I'm going to take that object, 3-kilogram object, as the object of my free body diagram. So I'm showing here, I'm imagining those 2 blocks are just part of something that's moving as a rigid unit, so why not throw them together? What forces are acting on it? Well, there's a weight force going down. This is a frictionless plane, so it can't push in the direction parallel to the plane, but it better be pushing perpendicular, otherwise these things would be in free fall. So there's a normal force going up on that 3-kilogram object, and then I have to also look at what forces are reaching in from the outside and pulling or pushing on this in the horizontal direction. And there's only one. we're pulling on the right-hand side with a force of 5 newtons. You know, there can't be any forces going in this direction because that would correspond to a friction force, kind of slowing it down. So there's a 5 Newton force reaching in from the outside and pulling on that 3 kilogram object, and it's directed to the right. So now let's, I've already given you in this problem, I don't know why, told you let's take plus x to the right. Maybe it's because it determines the signs of some things down below. So if plus x is to the right, and if I do F net x, or sum of the force x components, is equal to max, let's write that down. And now there's only one force with a non-zero x component, right? Plus x is to the right. As I move from tail to tip along this vector, I don't have to move along x at all, so its x component is 0. Same thing for the weight force. The only one that has a non-zero x component is this one, and its x component is positive. So F net x is just plus 5 newtons. That's equal to the mass of the object in the free body diagram, that's 3 in SI units, times the unknown AX. AX is how fast it's accelerating to the right, and I can solve for AX, 1.66666666 meter. There's a mistake here. Actually, I think in my scan, I had a square on there. The units of acceleration should be meter per second squared, but it got cut off when I scanned my solution. So AX is 1.67 in SI units. How does the force of string 1 on block A compare to the force of string 2 on block B? So string 1 is pulling on block A to the right. String 2 is pulling on block B to the right. Which one's bigger, or are they the same? And I believe that the hint says they are not equal, because a lot of people think, well, the accelerations are the same, the string forces have got to be the same. But no, look at this. String 1 is dragging behind it 3 kilograms that it's got to accelerate at this rate, whereas string 2 is only dragging behind it 2 kilograms that it has to accelerate at this rate, so it doesn't have to pull as hard. So how are we going to find, well, that answers that. Force in string 1 has got to be greater because it's accelerating 3 kilograms. String 2 is only accelerating 2 kilograms, and it's at the same rate of acceleration. So string 1's force has to be greater because it's accelerating a greater mass. Now, this is a reminder that I want you to actually figure out the answers to these 5 other parts to the problem. How am I going to find what the tension is in string 1? Well, I already found the acceleration of this 3 kilogram object. I could do F net equals ma x components, just like I did over there. And essentially, I know the A and I know the M, so that's going to tell me what Fx has to be. But I already knew that Fx was 5 newtons. So in other words, the tension in string 1 is nothing. It's the same as the force that string is exerting on my finger as I pull it here. But that's the same as the force that my finger is exerting on string 1. That's just Newton's third law. So by virtue of pulling on this string with a 5 Newton force, I'm setting up a 5 Newton tension in the string, and that means the string 1 is pulling on block A with a 5 Newton force. So that's the answer to C. That's not so simple when you start talking about string 2. So I want you to try to answer the other 5 parts to this, and we'll be back with the solution.